Welcome to our comprehensive journey through the world of electronic circuits and their applications. In this unit, we'll explore the essential building blocks that power modern electronics, from rectifiers and amplifiers to oscillators and integrated circuits. Whether you're a beginner or looking to refresh your knowledge, this series will break down complex concepts into easy-to-understand segments. Let's start by understanding why circuits are so fundamental to technology and how they form the backbone of everything from smartphones to industrial machines. Get ready to dive into the fascinating world of electronics. Rectifiers are crucial components in electronics, converting alternating current AC into direct current DC. This process is vital because most electronic devices require DC to operate. Imagine plugging your phone into a wall socket inside the charger. A rectifier is hard at work, ensuring your device gets the right kind of power. There are several types of rectifiers, each with unique characteristics and application. In the next scenes, we'll break down the main types, half-wave, full-wave, and bridge rectifiers, and see how each functions in real-world circuits. Half-wave rectifier is the simplest form of rectifier. It allows only one half of the AC waveform to pass through, blocking the other half. This means that only the positive or negative portion of the input signal is used, resulting in a pulsating DC output. While not very efficient, half-wave rectifiers are often used in low-power applications where simplicity and cost are more important than performance. Let's look at how a diode plays a key role in this process and why this configuration is a stepping stone to more advanced rectifiers. Like the half-wave rectifier, a full-wave rectifier utilizes both halves of the AC waveform. This is achieved by using two diodes and a center tap transformer or four diodes in a bridge configuration. The result is a smoother DC output, making full-wave rectifiers much more efficient and suitable for higher power applications. They are commonly found in power supplies for various electronic devices. Understanding the full-wave rectifier is key to grasping how modern electronics manage power conversion efficiently. Bridge rectifier is a popular full-wave rectifier design that uses four diodes arranged in a bridge configuration. This setup eliminates the need for a center tap transformer, making it more compact and cost-effective. The bridge rectifier efficiently converts the entire AC input into DC output, providing a steady and reliable power source for many electronic circuits. Its widespread use in power adapters and chargers highlights its importance in everyday electronics. Clippers are circuits designed to remove or clip portions of an input signal without distorting the remaining part. They are often used to protect sensitive components from voltage spikes or to shape waveforms for specific applications. For example, in audio electronics, clippers can prevent signals from exceeding a certain threshold, ensuring clear and undistorted sound. Understanding how clippers work helps in designing circuits that require precise voltage control. Clampers are circuits that shift the entire voltage level of a signal without changing its shape. This is useful in applications where a signal needs to be moved up or down to match the input requirements of another circuit. For instance, clampers are used in television receivers to restore the DC level of video signals. By understanding clampers, you can design circuits that ensure signals are always within the desired voltage range. Voltage multipliers are circuits that increase the voltage of an input signal without the need for a transformer. They use a combination of diodes and capacitors to achieve this effect. Common types include doublers, triplers, and quadruplers, each multiplying the input voltage by a specific factor. Voltage multipliers are widely used in devices that require high voltage but low current, such as cathode ray tubes and photomultiplier tubes. Voltage multipliers find their place in a variety of applications where high voltage is needed but current demand is low. For example, they are essential in powering the display tubes of old televisions and oscilloscopes. They also play a role in scientific instruments and medical equipment. By efficiently stepping up voltage, these circuits enable devices to function without bulky transformers, making them more compact and lightweight. Amplifiers are circuits that increase the amplitude of a signal, making weak signals strong enough for further processing or output. They are found in everything from radios and televisions to audio systems and medical devices. The basic function of an amplifier is to take a small input signal and produce a larger output signal, all while preserving the original information. Next, we'll look at the most common amplifier configurations and how they work. Common emitter CE amplifier is one of the most widely used transistor amplifier configurations. In this setup, the emitter terminal is common to both the input and output circuits. CE amplifiers provide good voltage and current gain, making them ideal for audio and radio frequency applications. Their ability to invert the input signal and deliver significant amplification makes them a staple in electronic design. Common source CS amplifier is the field effect transistor FET counterpart to the CE amplifier. Here, the source terminal is common to both input and output. CS amplifiers are known for their high input impedance and are often used in applications where minimal loading of the previous stage is required. They are especially useful in radio frequency and audio circuits, providing both voltage gain and signal amplification. Amplifiers are at the heart of countless electronic devices. In audio systems, they boost sound signals to drive speakers. In communication systems, they amplify weak radio signals for clear reception. Medical equipment relies on amplifiers to detect and process tiny biological signals. The versatility and importance of amplifiers make them a foundational topic in electronics. Oscillators are circuits that generate repetitive waveforms such as sine, square, or triangle waves without any external input signal. They are essential for producing clock signals in computers, generating radio frequencies, and creating audio tones. Oscillators come in various types, each suited for specific applications. Next, we'll explore the main types: RC, LC, and crystal oscillator. RC oscillators use resistors and capacitors to produce oscillations. They are commonly used for generating audio frequencies and as timing elements in electronic circuits. RC oscillators are valued for their simplicity and ease of design, making them ideal for low-frequency applications such as tone generators and timers. C oscillators rely on inductors L and capacitors C to generate oscillations, typically at higher frequencies than RC oscillators. They are widely used in radio transmitters and receivers where stable and precise frequency generation is crucial. LC oscillators offer better frequency stability and are a key component in communication systems. Crystal oscillators use the mechanical resonance of a vibrating crystal, usually quartz, to generate highly stable frequencies. These are essential in applications where precise timing is required, such as in watches, computers, and communication equipment. Crystal oscillators are prized for their accuracy and reliability, making them the standard choice for clock generation in digital systems. Oscillators are found in a wide range of devices. They provide clock signals for microprocessors, generate carrier waves for radio transmission, and create tones in musical instruments. Their ability to produce consistent and reliable signals makes them indispensable in both analog and digital electronics. Integrated circuits, or ICs, are tiny chips that contain thousands or even millions of electronic components, such as transistors, resistors, and capacitors, all packed into a single package. ICs have revolutionized electronics by enabling complex functions in compact, reliable, and affordable forms. They are the brains behind computers, smartphones, and countless other devices. IC fabrication is the process of manufacturing integrated circuits. It involves multiple steps including doping, etching, and layering materials on a silicon wafer. The process is carried out in ultra-clean environments called cleanrooms to prevent contamination. Advances in IC fabrication have led to smaller, faster, and more energy-efficient chips, driving progress in technology. Rectification is a fundamental process in electronics, converting AC to DC so that devices can function properly. Without rectifiers, many of our everyday gadgets would not be able to operate. Understanding rectification helps us appreciate the importance of power management in electronic systems and the role of basic circuit components. Comparing half-wave and full-wave rectifiers highlights the trade-offs between simplicity and efficiency. While half-wave rectifiers are easy to design, full-wave rectifiers provide better performance and smoother DC output. Choosing the right type depends on the application's power requirements and design constraints. Bridge rectifier stands out for its efficiency and practicality. By using 4 diodes, it eliminates the need for a center-tap transformer and provides full-wave rectification. This makes it a popular choice in power supplies for consumer electronics, offering a balance of performance and cost-effectiveness. Clippers are used in various scenarios such as protecting circuits from voltage spikes or shaping audio signals. By removing unwanted portions of a waveform, they help maintain signal integrity and prevent damage to sensitive components. Their role in signal conditioning is vital in both analog and digital systems. There are several types of clippers, including series and parallel configurations. Series clippers use a diode in series with a load, while parallel clippers use a diode in parallel. Each type offers different clipping characteristics, allowing designers to tailor circuits for specific needs. Clampers can be positive or negative, depending on whether they shift the signal upward or downward. Positive clampers add a DC level to move the signal up, while negative clampers move it down. This versatility makes clampers useful in a wide range of applications from audio processing to instrumentation. Voltage doubler is a specific type of voltage multiplier that doubles the input voltage using diodes and capacitors. It's commonly used in power supplies where a higher voltage is needed without increasing transformer size. Voltage doublers are efficient and simple, making them a practical solution in many electronic designs. Beyond doublers, there are triplers and quadruplers which multiply the input voltage by 3 or 4 times, respectively. These circuits are constructed by cascading multiple stages of diodes and capacitors. They are essential in applications where high voltage is needed but current demand is low, such as in scientific equipment. Amplifiers can be configured in various ways to suit different applications. Besides common emitter and common source, there are common base and common collector configurations for transistors, and common drain and common gate for FETs. Each configuration offers unique advantages in terms of gain, input, and output impedance. Frequency response of an amplifier describes how it amplifies signals of different frequencies. A good amplifier maintains consistent gain across the desired frequency range. Understanding frequency response is crucial for designing audio systems, radio receivers, and other applications where signal fidelity matters. At the heart of every oscillator is the concept of positive feedback, where a portion of the output is fed back to the input in phase. This feedback sustains oscillations, allowing the circuit to generate continuous waveforms. Understanding feedback is key to mastering oscillator design. RC oscillators come in several varieties, including phase shift and Wien bridge oscillators. Each type uses a specific arrangement of resistors and capacitors to achieve the desired frequency and waveform. These oscillators are especially useful in audio and signal generation applications. LC oscillators include Hartley and Colpitts designs, each using inductors and capacitors in unique configurations. These oscillators are preferred for generating radio frequencies due to their stability and tunability. Understanding the differences helps in selecting the right oscillator for your application. Crystal oscillators operate by exploiting the piezoelectric effect of quartz crystals. When an electric field is applied, the crystal vibrates at a precise frequency, producing a stable oscillation. This property is why crystal oscillators are the standard for timekeeping and frequency control in electronics. Degraded circuits can be classified as analog or digital. Analog ICs process continuous signals such as amplifiers and oscillators, while digital ICs handle discrete signals like logic gates and microprocessors. Many modern ICs combine both analog and digital functions in a single chip. Fabrication of integrated circuits involves several key steps: wafer preparation, oxidation, photolithography, doping, etching, and packaging. Each step must be precisely controlled to ensure the performance and reliability of the final chip. Advances in fabrication technology have enabled the production of ever smaller and more powerful ICs. IC fabrication takes place in cleanrooms, which are highly controlled environments designed to minimize dust and contaminants. Even a tiny particle can ruin a chip, so workers wear special suits and the air is constantly filtered. Cleanrooms are essential for producing high-quality integrated circuits. After fabrication, ICs are packaged to protect them from physical damage and environmental factors. Packaging also provides the necessary connections for the chip to interface with other components. The choice of package depends on the application, with options ranging from simple dual inline packages to advanced surface mount designs. Integrated circuits are everywhere, from computers and smartphones to cars and medical devices. Their ability to perform complex functions in a small space has transformed technology and enabled the development of modern electronics. Understanding ICs is key to appreciating the power of today's devices. Future of electronic circuits is exciting, with ongoing advances in miniaturization, speed, and energy efficiency. Emerging technologies like quantum computing and flexible electronics promise to push the boundaries even further. Staying informed about circuit fundamentals prepares you for the innovations ahead. In this unit, we've covered the essentials of rectifiers, clippers, clampers, voltage multipliers, amplifiers, oscillators, and integrated circuits. Each component plays a vital role in modern electronics, enabling devices to function efficiently and reliably. Mastering these basics lays the foundation for more advanced study and practical applications. Applying what you've learned, you can start designing simple circuits using rectifiers, amplifiers, and oscillators. Experimenting with these components helps solidify your understanding and prepares you for more complex projects. Remember, hands-on practice is the best way to master electronics. Safety is paramount when working with electronic circuits. Always follow proper procedures, use insulated tools, and double-check connections before powering up a circuit. Understanding the risks and taking precautions ensures a safe and productive learning experience. There are many resources available for learning more about circuits and electronics. Books, online courses, and simulation software can help deepen your understanding. Joining electronics communities and forums is also a great way to get support and share ideas with others. Congratulations on completing this unit. You now have a solid foundation in the basics of electronic circuits and their applications. Continue exploring, experimenting, and building your knowledge. The world of electronics is vast and full of opportunities. Your journey has just begun.